Welcome back class to our course on mechanical behavior of materials part 2. So in the last lecture, we discussed about high cycle and low cycle fatigue, and we talked about Baskin equation and Coffin-Manson equation. Okay. So we have till now, we have discussed about ascent curves and low cycle and high cycle fatigue. And from today, we will talk about the mechanisms of fatigue damage. Okay, that means we'll talk about how the fatigue crack initiate and then it propagates and finally leads to the fracture. Okay, so let's proceed. So we'll talk about process of fatigue damage. Okay. So we are going to have initiation, okay, and then propagation. So first, the fatigue crack has to initiate, and once it has initiated, it has to propagate, which will lead to the fracture of the sample. Okay. So in initiation, we will discuss about effect of surface defects such as scratches, notches, cracks, etc. Okay. And then we'll also talk about something called persistent slip band. So I'm summarizing what we are going to discuss in the next 1 or 2 lectures, okay, where we will talk about extrusion and intrusion. In propagation, we will discuss about stage 1 fatigue crack growth, then stage 2 fatigue crack growth, and finally stage 3 crack growth, which will lead to the fracture, fatigue failure. Okay, so we'll start today with the initiation, and finally we will talk about how fatigue crack propagate in a sample in fatigue loading. Okay, so let's talk about initiation. So in initiation, we'll start with the surface defects, right? So whenever you have some material, some components or some samples, you are going to have scratches, right, on the surfaces, some defects, some flaws on the surfaces. And these flaws are very important because from these flaws, you are going to generate fatigue crack. These will act as a nucleation sites for fatigue crack. Okay. So there will be several small cracks, flaws on the surface. Of sample. So if you're doing fatigue test, right, you're having samples, they will be having lots of flaws on the surface defects. Okay. Now these surface defects, they are going to act as stress razors. We have discussed about this before when we are talking about stress concentrations, right? Okay. Suppose you have a surface and there is a flaw here like this. In this case, it's a notch. Suppose it's a notch. Even the crack will be something like this or scratches, right? Now, if you see this, right, there will be stress concentration in front of this surface defect, right? And because of the stress concentrations, you are going to see what stress concentration here. Okay. And because of the stress concentration, you can nucleate fatigue crack. Okay. So crack, because of the stress razors, you are going to generate stress concentration. And this can lead to crack initiation at these locations. These locations means at the surface flaw, which are acting as stress razors. Okay. So remember that, even if your material is or your sample is under elastic loading, right? These stress razors can enhance the stress in front of this defect to a great extent that the crack can initiate. Okay, even though your applied stress is below yield point. And that is why I mentioned when I started talking about fatigue failure, this topic, I mentioned that that it is very dangerous because fatigue failure can occur even if the applied stress is below yield point. Okay. So it should be noted that even if material is under elastic loading, right, that means say below yield point, stress amplification at these stress razors, which are defects, surface flaw. Okay. So stress amplification at these stress razors could lead to crack initiation. Okay. So this is important that it is below yield point, but because of the stress concentration, you can have crack initiation. Okay. And finally, it is going to propagate, which could lead to the failure. So this is one of the mechanisms how fatigue crack initiates. You have to have a surface flaw. Okay. Now, what happens when you don't have surface flaw? Suppose you polished it very smoothly, your sample, right? Say you electro polished it, so you have removed most of your surface defects, right? Then how do you generate fatigue crack, right? That question will come into your mind, right? So let's talk about that. So the question is, if the sample surface is smooth, we are saying that there is no flaw. Okay. So what will happen? Remember, before your material is going to show macroscopic yielding, there can be microscopic yielding locally, right? Depending upon the drain orientation with respect to the loading axis direction. Okay, so some of the drains are going to be favorable towards the loading axis or loading direction, and those drains they are going to slip first, right? So there could be microscopic yielding before you see macroscopic yielding in a given sample. Okay, we have discussed this also before when we were talking about Luder band. If you go to the course number 1. So prior to macroscopic yielding, microscopic yielding can occur in drains which are favorably oriented with respect to loading axis. So you can correlate this with respect to Smith factor. Okay, so some of the grains are going to yield before you see macroscopic yielding. Okay, so that means you are going to have local plaster deformation before yield point. Okay, and when this happens, you are going to see formation of persistent slip band, and this happens in fatigue loading. Okay, so what is happening here? Since you are talking about fatigue loading, you have a cyclic loading, right? So you are going to have slip reversal during each cycle. Okay, so in cyclic loading, due to reversal of slip, okay, you are going to form intrusions and extrusions. And these intrusions, they are actually small surface cracks. So they are like small surface cracks. Okay, so persistent slip band will have intrusion and extrusions. And if you further, have more number of cycles, cracks are going to form or nucleate at these intrusions. So with more cyclic damage, cracks nucleate at intrusions. I will show you the schematic so that you can understand it better. Okay, so let's see, you have a sample, okay, and what you are going to form is persistent slip band, and in that you are going to have extrusion and intrusions. Okay? So it's going to be something like this. Eventually, I'm going to show you the microstructures or micrographs of all these persistent slip band, intrusion, extrusion, and later on I will discuss about beach mark, striation. So all together, I'm going to show you all those in one lecture. Okay. It's something like this. So this is under applied stress of delta sigma. Okay. And remember, this is delta sigma. So you're talking about fatigue. Okay. So there is a cyclic loading. It's not uniaxial. So if it was uniaxial, remember there will be slip along only one direction, right? There will be no slip reversal. Here, since you are talking about fatigue, you are going to have slip reversal. And that's why you're going to get a structure something like this, what I've drawn here, right? And this is called persistent slip band, where you have extrusion and intrusions. So this part here, this is called extrusion. It is like extruding out from the surface. So it is called extrusion. And the part which is inside, this guy here, this is intrusion. So it is inside. Okay? And this is your sample surface. And the whole thing here is your persistent slip band. Okay. So persistent slip band leads to extrusions and intrusions. Okay. So you are going to have slip along these lines. So these are your bands. These are called persistent slip bands, right? So you have lots of dislocations in these bands. Okay. And since because you have slip reversal, you are going to get both extrusion and intrusions. Okay. If it was uniaxial tension, you're not going to get extrusion and intrusions, right? It is only because since you have cyclic loading, you're going to get that. Now this intrusion, if you see, if you just magnify this is acting like a notch, small notch on the sample surface. Right. So if I just, draw another schematic, so this is what you are going to see, right? You just blow this region here. Okay, so this is your extrusion and this one is your intrusion. I have removed persistent slip band. Okay, so these intrusions, they are going to act as a notch. They are going to act as stress razors. Okay, now remember, this was not there before. This is happening on the polish sample, electropolish samples where you don't have any flaws, right? But because of the cyclic nature of loading, you're going to form extrusion and intrusions. And these intrusions, they are going to act as stress razors. And then you're going to apply the same concept what we just discussed when you have surface flaws, right? So now from these inclusions, you can nucleate fatigue crack. You can generate fatigue crack. Okay? So these intrusions, right, can nucleate . fatigue crack. Okay, so I hope you have understood the concept of persistent slip bands. Okay, these are slip bands and these are called persistent slip bands, right? And when they form also extrusion and intrusions. Okay, and intrusions are going to act as surface stress razors. Okay, now let me summarize. So what is happening here? If you have a surface, so you are going to have and then something here. Okay, so this is your sample surface. Okay, and then you are going to have small cracks. Say these are nucleated. Okay, so these blue lines, these are nucleated fatigue crack. Okay, now let me magnify each one of them. So let's see, I'm talking about this here. So if I just magnify it, what you are going to see is something like this. Okay, so these are your intrusions and extrusions, right? And persistent slip bands are there, and you are generating a crack. So let me use the same color blue. So this is your crack, fatigue crack. Okay. So I'm just showing you the magnified version. Okay, so crack is nucleating from the intrusion. Okay, now let me blow the another one. Say if I just blow it, you have the surface, and then there is a small notch, and from this notch, you are generating a crack. So this is your fatigue crack. And this guy here is your notch, the surface notch. Okay, so these are the two mechanisms we have discussed. One is because of the surface flaw, which is the bottom one. Another one is because of the slightly damage. Because of the nature of the fatigue loading, you are going to form intrusions. Okay, and then from there, nucleation of the fatigue crack occurs. Now, the third mechanism, which I have shown here, this is like internal defect. Internal defects or flaws, right? Such as, you have porosity, second phase particles. So when you have these internal defects, they can also act as a nucleation site for fatigue crack nucleation or fatigue crack initiation, right? So if I just blow it, it will look like something like this. So you have this the inclusion, say the second phase particle, which is inclusion, and then you have this crack. Okay, so these are your fatigue crack, which has nucleated. And this is your internal defect. Okay, so we have discussed how fatigue crack initiate in a given sample. So it can initiate from the surface, and most of the books actually mention that the fatigue crack predominantly initiates from the surface. There are two mechanisms: one from the flaws already present, or second because of the formation of intrusions. Okay, because of persistent slip bands. And second, it can also form from internal defects. Okay, So in the next lecture, we'll start talking about the mechanisms of fatigue crack propagation. Okay. See you next class. Thank you.